Hi everyone, my name is Miss Dunlevy. I'm here today as a guest for your physical science class. I've been learning about the things you guys have been studying. I'm very excited to hear about them, and I'm hoping we can incorporate some of the things you've been learning recently into our lessons today, have some fun with them, and really play around with the concepts. So before we dive right in, let's talk about this video that we watched earlier, right? I want you to keep this video in the back of your mind as we talk about the concepts later today. This whole chain reaction started with a single marble, and I asked you to think about how it's possible that a single marble resulted in knocking over a chair or pulling a book off a shelf. What are some possible explanations from physics for how this is possible? I wanted you to think about that while you're watching the video, and I also want you to be thinking about that as we move forward. And as we move forward, I want to start with a review. So the first thing I want to review is the concept of work. You should be familiar with this already, but let's just recap. The idea of work is a force causing the displacement of an object. So work is forces causing the displacement of an object. And another way to describe that is a measure of energy transfer that occurs when an object is moved over distance by an external force. For those of you who like equations and they help you to understand, there's the equation for work at the bottom. Work equals force times distance. If you're familiar with this concept, you've got it down, give me a thumbs up. If you need a review, give me a thumbs down. And if you're in the middle, give me a thumbs to the side. All right, we've all got this concept down. We understand that work is force over displacement, so force over a distance, and that gives us work, and work is a measure of energy. So with that in mind, let's learn a new term. Our new term today is mechanical advantage. A mechanical advantage is defined as the ratio of the force produced by a machine versus the force applied to it. So force produced versus force applied. It's another way of describing it is the measure of how much a force is increased by using that tool or machine. So looking again here, we have an equation, output force over input force equals mechanical advantage. All right, so it's a ratio of how much force we're getting out versus how much force we put in. If we think about that picture, that video in the beginning, we can think about at each step, maybe there's some mechanical advantages involved. We're starting to put some pieces together there. If you understand mechanical advantage and you're ready to move on, give me a thumbs up. If you're not tracking with me at all, give me a thumbs down. And if you understand what I'm saying, but you're not sure how to apply it, give me a thumbs to the side. All right, I'm seeing a lot of thumbs up, a few thumbs to the side. That's okay. What I want you to remember right now is if you're not sure how to apply it, just remember that mechanical advantage means output force over input force. How much force we're getting out versus how much force we're getting in. And a bigger output force for a little input force means we're getting a big mechanical advantage. All right, so that's what I want you guys to keep in mind as we move forward. So here's our question. Let's just put those two concepts together, the concept of work and the concept of mechanical advantage. Thanks to mechanical advantage, our output force is greater than our input force, right? Greater than our input force. And as a result, the distance over which we apply that force needs to what? Increase, decrease, or stay the same. The distance over which we apply that force increases, decreases, or stays the same. Go ahead and give me an answer on Kahoot real quick. I put that force equation or the work equation at the bottom for you to review. Great. I'm getting a lot of people right away saying that this distance should increase. For those of you who aren't quite sure, maybe you're not exactly sure where that's coming from. Work is a measure of energy, and energy is conserved. So assuming this is a perfect system and for the same task, right, the amount of work needs to stay the same. So if the distance if the force is decreased, the amount of force that we are putting in decreases, the amount of distance over which we apply that force has to increase to keep the amount of work the same. So for any given task, we know this, the work has to stay the same. If we have a box that starts on the ground and then it goes onto the table, no matter how it gets there, it's got to be the same amount of work. All right? And in order to do that, if the force goes down, the distance has to go up. All right? So what are some ways to apply this concept? The idea that we apply a smaller force over a larger distance. Well, those would be our simple machines. I'm sure you guys have seen these before, but let's just do a quick review. Simple machines are physical devices that change the direction or magnitude of a force. It doesn't have to be both, but a lot of times it is both. Changes that direction or the magnitude of a force. A device that does that is a simple machine. They do not change the amount of work that is done. Going back to that box example, if we use a simple machine to move that box from the ground to the table, the amount of work stays the same, but the way it feels may change by creating a mechanical advantage or by changing the direction of the force. Let's look at some examples of that. This I'm sure you've seen before. You've probably done some force equations with it. This is an inclined plane. Great. So this is an inclined plane. Let's talk about that box again, right? Say this box is on the bottom here, and we need to move it to a table that's at this level. If I pick this box up and I put it on the table, that's a small distance, so it's going to require a decent sized force, right? Now, if I pick this box up and put it onto this ramp and I slide it up to the table, that's a longer distance, so that means the force required to push it up the ramp, assuming it's a frictionless ramp, is going to be decreased. And that's the basic principle of inclined planes. All right, so inclined planes are ramps. They could be slides. They could be other things that we find that we use that principle. Longer distance. This is the most simple way of using longer distance and less force to move an object to get the same amount of work done. So who can give me another example of an inclined plane other than a ramp or a slide? Excellent. That's a great example. So an example that they listed was a curb. So when we use a curb that is slanted to allow somebody to just roll over it, that would be an example. Another example that you might not think of right away is a ladder. If we lean that ladder up against the building, even just a slight angle will help improve our ability to get up that ladder by increasing the distance that we need to go up. All right. How about this? We have I know you guys know what this is. This is a screw, right? Well, what you might not realize is the screw is actually an inclined plane that's wrapped around a cylinder. All right, so if we have an inclined plane wrapped around a cylinder, again, we're applying a force over a greater distance. And some examples of that are obviously screws and bolts. But can anybody think of another example of where we would use a screw? Yeah, like a lid of a jar or a water bottle, something like that. That's a screwing mechanism as well. All right. How about this one? This one we can see is a piece of wood, right? So it looks like an axe. But what would we call this type of simple machine? This one you might not have remembered this one. We call this a wedge. And if you look and we drive a midpoint down through this wedge, it's actually two inclined planes butted right up against each other. All right, now wedges are used to drive things apart, right? And they're also used to keep things from moving. You could think of a doorstop in this regard. All right, so what are some other examples of wedges? A chisel would be another example, very similar to an axe, but on a much smaller scale. And maybe you're not thinking about these right away, but most blades, right? Nails, knives, staples, they all have little tiny wedges at the bottom so to help you, really narrow wedges to help you drive them into the thing that you're looking to separate, right? Those are all examples of wedges. Now, if you're just tracking along with me here, we're just doing a quick review. We're going to talk more this week about how we can define the mechanical advantage created by all these devices, but today I just want us to review, all right? So we're just remembering the types of simple machines and how they work. This one we should all be familiar with is a lever, right? So the lever has two parts. There's a bar, and then there's a fulcrum, or it's a pivot point. Some examples of levers, I'm sure you guys know the seesaw example, but what's another example that we could use? That's a good example, a crowbar, or maybe the back end of a hammer, right? We have a pivot point created by that curve, and then we put force on the one end all the way, and it pulls on a short little end. It pulls that nail right out of the wood. So that's an example of a lever. Maybe one that you didn't think of would be a door, right? A door is actually a type of lever, right? We pull the door on the far end, and it turns at the pivot point. So that's an example of lever action as well. All right, this one we see all the time. This one is a wheel and an axle, right? So other than wheels and axles, and tires and things like that, what are some other examples of wheels or axles that we could use? How about like a spool of thread? Or a pizza cutter. A pizza cutter is another example. And I'm pretty sure we're all familiar with the idea of a wheel or axle. Moving things by rolling them is a lot easier than sliding them across a bare floor, right? So we're familiar with how that might create some mechanical advantage for us. Now, I misspoke just a second ago. I listed spools as a wheel or axle, but really it's a very specific type of wheel or axle, right? That's a pulley, right? So we could say that it's technically a wheel or axle, but it might be better to say that it's a pulley, because a pulley is a wheel or axle with a groove for rope or thread to go around. Now, pulleys are a great example of both. We talked about simple machines being able to create a mechanical advantage to reduce the amount of input force needed, and also being able to change the direction of a force. So pulleys are a great example of how we can do both of those things. We can both move, instead of pulling up this bucket, we're pulling down on the rope. And we're also using less force than is necessary to pull up on the bucket, because we have this angle, meaning that we can pull over a greater distance instead of pulling straight up. So that's an example of how we can both change the direction and magnitude of a force. All right. So really quickly, let's just review, how might we be able to put some of these machines together into a compound machine? A compound machine is more than one simple machine put together. Here's some examples. Really quick, let's go. All right, this is a wheelbarrow. What types of simple machines can you spot used to make a wheelbarrow work? Right away, I'm seeing wheel and axle. We're noticing that wheel and axle right here. But if we look and we pay attention closely, we notice that there's a pivot point right here, right, for this lever arm. And this is an example of a lever. So we have a wheel and axle, and we've got a lever combining to create a compound machine of a wheelbarrow. Let's look at another one. All right, based on that last one, I think we're all noticing this fulcrum right here for our lever arm. What other type of simple machine are we noticing? This one's a little tricky, but those edges of the scissors right here, those are wedges. They help us to separate, right? Remember, that's one of the principles of wedges. They help us to separate that paper. So those are wedges. Those sharp edges are wedges. Last one, a bicycle. What types of simple machines do we see? All right, we've got right away wheel and axle. Very good. Pulley. I'm seeing pulley come in. How about a lever as well? Some of you got this, but the lever for the steering. We're able to use that lever action to control the steering for the front wheel. All right, very good application. Let's go ahead and do this for ourselves. We're going to make our own compound machines. We're going to incorporate those simple machines. And while we're doing that, I want you to be thinking about the mechanical advantage that you're using when you're creating your chain reaction systems. We're going to design a trick shot chain reaction system of at least 10 steps. Each step has to be a new type of action. So if you put 100 dominoes in a row and you knock them all over, that's great, but that's still one step. All right? You need to include at least 4 of our 6 types of simple machines, which, as a reminder, were our inclined plane, our screw, our wedge, our wheel, our pulley, and our lever. All right? So 4 of the 6 you have to include, and the machines must be confined to your lab tables. At the end, it must result in a ping pong ball landing in your team's cup. You're going to get 30 minutes to do this, and while you're doing it, again, I want you to be thinking about the mechanical advantages that you're creating with the use of the simple machines to enable a trick shot chain reaction system. So go ahead and get into groups. I'm going to come around and ask some questions and just see how you're doing. All right, let's wrap up real quick. You guys have all got your stuff put away, but let's just take a minute and think, pair, share. What I want you guys to do is think about an answer. Then we're going to pair up into partners and talk about it. And then you're going to pick one from each partner to share with the class about what you think the answer should be. So which types of simple machines were the hardest for you to incorporate into your chain reaction systems, and why? What was the hardest to incorporate, and why was it hard to incorporate into your chain reaction system? All right, so go ahead and think, then pair, then share. All right, great. So I did want to mention, before we kind of close for today, we had a really good discussion about what types of simple machines are more commonly used and which ones aren't. Some people don't think that these 6 simple machines are the only simple machines. Some people might include a gear as another type of simple machine. Some people may say there's even less than 6, because technically things like the pulley is a special kind of wheel or axle, and a screw is a special kind of inclined plane. So these are not the only things we can define as simple machines. We're just talking about them just to kind of get an idea in our head about what simple machines can do and how they can create a mechanical advantage. And we're going to go deeper into that this week. We're going to talk about the specifics of each machine. But for your homework this week, I want you to be working on sketch a chain reaction system your team created. You can do a hand sketch, a digital sketch. Then I want you to label the simple machines that your team chose to include, and I want you to pick one of those simple machines and describe in your own words how that type of simple machine can give us an increased mechanical advantage. Remember, we're going to look more into that later, but have a great day.